So during the ice sheet, we reviewed a little bit with solving simple systems of equations. So this is very nice for us to do using substitution elimination when we only have a few variables, but it's going to very quickly get tedious when we've got systems of equations that have even more variables. So up until now, we've just kind of been going a little ad hoc, just kind of trying some stuff, seeing how it works. And what we're going to do in this section is we're going to set up some of our key terms for the semester. We're also going to discuss an algorithm that's going to help us solve larger systems of equations. Now this algorithm is a little bit weird, it's a little tedious, but the nice thing is we're going to be able to have a computer program do this for us. So it's going to allow us to program a computer to do these systems of equations for us. So our main focus won't be necessarily us hand solving a lot of these systems of equations, but it'll be more focused on us being able to take the solutions to a system of equations and use programs to solve those and then interpret those results. So let's get started with some terms. First definition, a linear combination of variables, x1 through xn, these are going to be our variables, is an expression of the form a1x1 plus a2x2 plus a3x3 plus, you can use your imagination what happens in between that and the last term, which would be an xn. Now remember, if you've seen summation notation before, we could rewrite this as a summation from I equals 1 to n of a sub I x sub I. And when we write this linear combination, the a sub i's are real numbers, which are called the combination's coefficients or scalars. So some examples of linear combinations would be something like 3x1 plus 2x2 plus 4x3 plus 7x4. We also don't even need to have all of our variables used. We could have more variables and some of the coefficients be 0. So something like 3x1 plus 2x2 plus 4x7 plus 5x9 minus 10x20. We also don't need to make sure we use this subscript notation. So there are a lot of things we could use for our linear combinations. For example, we could use 3x plus 2y minus z. We also don't need to have a bunch of variables. We could just have something on its own, x6. However, there are some things that aren't examples of linear combinations. So notice that for our unknowns, our x sub i's here, our x, y, and z's, each of these have a power of 1. We don't write it because we don't typically write a power of 1. So some non-examples would be things that are non-linear. So like 5x1 squared plus x2. Here when we write this, our squared on the x1 is causing us to not be linear. Similarly, we could write 7x1 x2 plus x3. Now if we write this, notice that we're taking x1 times x2. So this is no longer a linear term, so we don't have that, and that won't work. Also keep in mind when we talk about linear combinations, everything has to be attached to a variable. So if we had something like x1 plus 5, this plus 5 is going to cause a problem because the 5 has no variable attached to it. Some other things that won't work, something like 5x1 over x2. Again, this fractional thing will make it nonlinear. 7e to the x plus 2y. So again, exponential term, not linear. And one more example, something like trig functions. So cosine of x1 plus 72x2 would be nonlinear due to this cosine portion. Now we can turn a linear combination into a linear equation by adding an equals b sub I. So this would allow us to create a system of linear equations. So we've kind of seen this already before. But the idea is that we have a number of linear combinations over here, and each of them is equal to some constant on the other side. So this part on this side is where we put our constants. And note this is just constants. There are no variables here. A solution to a linear equation is going to be an n-tuple S1, S2, all the way through Sn, which solves each equation in the system. So if you remember in ICE 1, we talked about how we need to make sure when we have something that's solving a linear equation that every single equation is satisfied. So in this case, this would say that x1 should equal s1, x2 should equal s2, and so on and so forth, all the way until we got our xn equals sn. So these sn's here are going to be what those answers are. There'll be some sort of constant in most cases, but not always. We'll see some weird things that happen a little later on down the line. So what we'd like to be able to do is record our linear systems compactly. So if we have to go ahead and write x1, x2, x3, all the way through xn, and write each of these coefficients, and write all of these things on the other side of the equation, that's going to get a little tedious pretty quickly. So what we'll do is we'll write a coefficient matrix first. So this can go ahead and be a matrix that each of the entries stores each of these coefficients from our linear combinations for us. Now, we also can get an augmented matrix where we draw a line in between. It kind of denotes the equal sign here. And we take these constants that we had on the right and we put them on the other side. And so this will allow us to store all of our non-variable information in here pretty succinctly. And this tells us about our variables. So each column represents a variable. While our rows represent our equations. So here, this could be the column for x1, for x2, for x3, all the way through xn. And when we're talking about our rows, these are the rows for equation 1 and equation 2, all the way through equation m. So note that we don't necessarily need to have the same number of rows as columns. Some of our nicer systems will look like that, but that will not always be the case. Alright, so let's go through a couple of examples then of talking about writing a system as an augmented matrix. So what we're going to do is we're going to take a look at this system here, and we want to go ahead and turn it into an augmented matrix like this. So the first thing we need to do is check that this system has something where all the variables are on the left and all the constants are on the right. So notice that our form up here is everything with the variables on the left, constants on the right. So we check here, all of these terms in the first equation have their variables on the left, so that's good. Here our variables are on the left, constants on the right. This equation we need to adjust a little bit because we have a constant over here. So this will become 9x3 equals 4. All I did is add 4 to both sides in order to solve our problem. And this last equation is doing just fine. So now we want to go ahead and turn this into an augmented matrix. So we can kind of label these, if it helps. This is equation 1, this is equation 2, this is equation 3, and this is equation 4. So what we're going to do is for each of these equations, we'll go ahead and store what the coefficient is for each of our terms, x1, x2, x3, and x4. And then we'll need to have some sort of augmented part to store the constant portion on the other side. So, if we look at equation 1, we have 1x1 minus 3x2 plus 5x3 minus 2x4 equals 0. So that would be how we store this first equation into a row in our matrix. Now our second equation doesn't have any x1, so we put a 0, plus 1x2 minus 3x3 plus 0x4 equals 2. Our third equation, now that we've rewritten it, only has the 9x3. So in the x3 column we should write a 9, and all of the other coefficients in that row are 0. And that equals 4. And then our last row, we have 0x1, 0x2, 0x3, 1x4 equals 1. So a matrix, as we talked about in the lab, is a rectangular ordered array of numbers with m rows and n columns. So when we're talking about the number of rows and number of columns, we're saying we have m equations and n unknowns before the augment. And then we could have another column for the augment. So let's look at a little bit of another example. So we can go from this example from saying we have equations to a matrix, but we want to make sure we can go the other way as well. So let's say we wanted to go ahead and convert this system back, or this matrix, into a system of equations. So what we'll do is let's just give our variables names of x, y, and z. And so this will give us equation 1, this will give us equation 2, and this will give us equation 3. If you're watching the video at home, take a minute to pause and see if you can do this conversion before I kind of reveal what it ends up being. Alright, you're back? Great. So, for our first equation, we're told we have 2x plus 1y plus 0z equals 0. For our next equation, we're told we have 0x plus 3y plus 0z equals 6. And for our last equation, we're told we have x minus y plus z equals 0. When we solve this system, we're going to end up getting x equals negative 1, y equals 2, and z equals negative 1. This is equivalent to the system of equations from above. So we want to go ahead and make sure we can take this system, which is the same as this one, because in the end it has the same solutions, and write it as a matrix. So going from here to here. And these are things we can do both ways. I keep drawing the arrow one way, but really we can use this process either way. They're equivalent things. If we want to use the first row, we're saying we have 1x equals negative 1, 1y equals 2, and 1z equals negative 1. Wouldn't it be nice if there was some way to get this ladder system from this initial one, just by solving, instead of having to go ahead and solve by hand, and kind of get this nice form for the matrix? What's nice about this is we can kind of very easily see this is x is negative 1, y is 2, z is negative 1. And we can, if we can read what these columns and rows are telling us, that's going to be kind of a nice form for us. So we can kind of go from here to here and very quickly see what our solution is. It turns out there's a name for this nicest form. We're going to have to do a little bit of work and see a slightly less nice form to get to the really nice form. So we want some augmented matrix with the maximum number of zeros that doesn't change the solution of our original system. It turns out that there's an algorithm to go ahead and get this nicest form, and so let's talk about what that nice form means. So first we're going to talk about echelon forms. So a couple of definitions. The leading term of a row is the leftmost non-zero term in that row. If a row has all zeros, then we say it has no leading term. A matrix is an echelon form if every leading term is in a column to the left of the leading term of the row below it, and any zero rows are at the bottom of the matrix. So let's look at some examples and some non-examples. So here we've got some examples. So every term needs to have a leading term. So leading term, remember, is the leftmost non-zero term in a row. So here, this is the leftmost non-zero, and it is to the left of the leftmost non-zero term of the row below it, following that first thing, and here's the leftmost non-zero term. So we kind of get this nice pattern here. We've got these zeros, and we've got kind of this almost stair-step pattern going on. Here, when we look at these, here are our leading terms. So remember, leading term is the leftmost non-zero term in a row. And when we look, this one is to the left of the ones below it, and that's the last we have to worry about that, because the others are zero rows. And we said that zero rows are going to have to be at the bottom of the matrix, so we're good to go there. If we take a look at this matrix, this is a leading term, and this is a leading term, and every leading term higher up is to the left of leading terms in the lower rows, and the zero rows at the bottom. Here, we've got this nice thing where our leading terms are these, and they follow that pattern we want. This is actually a fun matrix called the identity matrix. But we'll get back to that at some point in the future. And here, let's identify first our leading terms. It'll be this, 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 and again they follow this nice pattern for us, where everyone is to the left of any of the ones below it. So there also are some things that aren't examples. So here, the first thing you'll want to do if you're trying to figure out if you're in echelon form is identify your leading terms. So these are going to be our leading terms. And if you'll notice, this one is to the left of this one, so this is what causes the problem. We identify our leading terms again. This one is going to cause some issues because it needs to be further to the right. Here, we have our leading terms worked out, but this zero row should be at the bottom. And here, I'm actually not sure why I said this was a non-example, is an example of echelon form. So this actually is an example. I'm not sure why I typed that there. My apologies. But it isn't reduced row echelon form. We'll see what this RREF stands for on a coming page. Alright, so when we're in an echelon form system, a pivot position is going to be an entry that corresponds to a leading term in the echelon form. So you'll have to kind of hang with me for this section. I know it gets a little tedious and boring. Variables that correspond to a pivot position are going to be called pivot variables. Now in the echelon form system, variables that are not leading are going to be free variables. I want to kind of highlight this. Free variables can give us infinite solutions. So if there was anything I was going to maybe highlight from this free variables portion would be the thing that I'd want to know. I don't know why. Usually later on in the class, people start getting weird ideas about what gives us infinite solutions, and in the end it's the pivot, or the free variables, the things that have no pivot positions, that give us infinite solutions. And we can maybe see that a little bit later. So if we wanted to look at this example, and we wanted to know which variables were pivots, then what we have to do is first identify our leading terms and identify which variables these are associated with. So if we're saying that this is the columns for x1, x2, x3, and x4, first of all, we should make sure this is in echelon form. So if we look, we've got our leading terms, we've got this nice pattern here, so it's in echelon form. So now we can go ahead and identify which are our pivot variables and which is our free variable. So our pivot variables are x1, x2, and x3, and our free variable is x4. So why is x4 a free variable? Well, it doesn't have any leading terms, and so it's going to be the free variable. Alright, so now we're going to say that a matrix or a system is in reduced row echelon form. This is going to be very important. We'll call this RREF if we want to go ahead and not write reduced row echelon form. So in order to be in reduced row echelon form, it needs to be in echelon form. So have that pattern we had from the previous page. All of the pivot positions have to contain a 1. And the only non-zero term in a pivot column is in the pivot position. So this is what we want. So some examples of reduced row echelon form would be this. So we've got leading terms, they are 1s, it's in echelon form, and we're good to go. And when we look at the non-zero terms in that column, it's only those 1s. Here we again have leading 1s, and then a row of all zeros, and we look up and down the columns, the only non-zero is the 1s, 0, 0, 0, 0. Here again, we've got these leading terms, they're all 1s, and they're zeros. So this last one, actually is also in reduced row echelon form. So in order to be in echelon form, if we remember, it requires us to have our leading term in the column of the leftmost left of the leading terms of rows below it, and any 0 rows are at the bottom of the matrix. And remember, leading terms are just the leftmost non-zero term in a row. In order to be in reduced row echelon form, it has to be in echelon form, which this is. Any pivot positions, which we have none, contain a 1. And the only non-zero term in a pivot column is in the pivot position. Again, don't have those. So this also is going to be in reduced row echelon form, which is kind of cool. So we want to think about which of these are going to be in reduced row echelon form. So A, B, and C. I want you to take a minute and see if you can determine this on your own. Pause the video and then come back. Also gives me a moment for a water break. Alright, assuming we're all back, first we need to identify our leading terms. This 5 and this 1. This is in echelon form, which is great. However, we have a 5 in this term, in this pivot position, and we need to make sure it's a 1 instead. So, this is in echelon form, but not reduced row echelon form. Let's take a look at the second matrix. So here we've got a 1 here as a leading term, a 1 here, and a 5 here. So note that this is not going to be in reduced row echelon form. We also don't have echelon form yet. We could do some things to get it there, but if this is going to be a pivot position, then we need to make this a 0. So this is not in echelon form yet. And in this last matrix, if you take a look, we've got leading term here is in echelon form. These are both 1s. Everything else in the column is 0. And so this is in reduced row echelon form. Cool, we got one. So this leads us then to Gauss's method for solving systems of linear equations. So it'd be nice if there was a way to take something that was in echelon form, or even better, reduced row echelon form, and have that be what we were given. However, what we want to do instead is take systems that aren't in this form and get them there. So if we only had 2 or 3 equations or variables, maybe it's not too hard for us to do a substitution and elimination. But even then, substitution and elimination, even for 3 variables, can get a little bit tedious. So lucky for us, there's an algorithm called Gaussian elimination. So let's talk about Gaussian elimination, also called Gauss's method, also called the Gauss-Jordan method. So if a linear system is changed to another by one of these 3 operations, then the 2 systems have the same set of solutions. In other words, they're equivalent. The 3 things we can do are swapping. So we can swap one row or equation with another. So we can say row 1, we're switching with row 2, and it'll help to write some things to kind of denote what we're doing. We can rescale an equation, so we can multiply one row or equation by a non-zero constant. So we can take row 1 and say it's becoming 3 times row 1. And we can also do a row combination. So we can take one row or equation and replace it with the sum of itself and the multiple of another row. So we can do something like row 3 equals row 3 plus 2 row 1. These 3 operations are called elementary row operations. And note that we can undo them. They're reversible. Now, I keep highlighting and underlining row here. There is a way to do things by changing columns instead of rows. However, that usually implies that you're writing things backwards. Now, there are a lot of videos online about linear algebra, and if you take a look at them and you're not careful, what'll happen is you'll see something that's doing some sort of method of Gauss's elimination, but with the columns. And that'll confuse you if you then come back to these notes and you're doing rows. So I'd recommend trying to make sure you're always looking at something that's doing row operations. So our basic strategy is we're going to replace our system of equations with an equivalent system of equations that's easier to solve. In the end, we want a matrix that is as close to a bunch of 1s along the diagonal with 0s above and below, and our solutions over on the right. This is helpful because then it's easy to see our solutions. So there's a little bit of a tie-in with our echelon forms. There's kind of 2 steps for Gaussian elimination. The first step is to get our matrix into an upper triangular form. So what we'll want to do is we'll want to try to get 1s along the main diagonal, 0s below, and we don't care so much about what happens above. This will give us our echelon form. And then we can go ahead and use our 1s at the bottom to substitute back up and eliminate things above in order to get that reduced row echelon form and get the 0s above the main diagonal as well. So note that every matrix's reduced row echelon form is unique. What this means is that no matter the order of your row operations, you should, put an underline should here, get the same answer every time. Now the reason I underline should is it's very easy, especially when you first start off with Gaussian elimination, to make some minor algebra mistakes. So be patient. If you tried something on your own and you make some mistakes and you don't get the same answer, even though you don't use the same order that maybe I use in the video, you know, it's kind of easy to make little tiny mental math mistakes. And I can almost guarantee I will probably make one by the time this class is over. And somebody will catch me on the video and I'll have to re-record the whole like 50-minute video or whatever. And nobody will be happy with that. So a way to help keep track and make sure you're doing things correctly is to write these little symbols for yourself to make sure you understand which row operations you did and you can kind of keep track of them. So let's try an example. So let's say we want to solve this particular system of equations. So what we want to do is we want to use the following steps. So just recap from the previous page. We want to get an upper triangular form. So remember that's kind of ones along the diagonals, zeros, don't care what's up here, and don't care so much about what's up here or over there. And then step 2, that is a 2, I promise, is to get reduced row echelon form by back substitution. So we want to go ahead and use those 3 row operations we talked about in order to get our leading ones. A-T-I-O-N-S. That's how you spell operations. So our operations are, we can swap rows, we can multiply rows by a scalar, and we can add a constant multiple of one row to another. Now, you can use whichever operation you want to do whatever you want. However, I'm going to kind of give you some free advice on what you should use for what part. Because we really have 2 things we want to do. We want to get leading ones, and we want to go ahead and later and get zeros. So these first 2 operations you should use to obtain leading ones. This is the only thing you want to do to obtain those leading ones. This last operation you should use to obtain zeros. So you'll kind of see that I won't end up using this other operation for most of what I have to do. So let's go ahead and start off with this matrix. So we want to be able to get a 1 in this top left corner. So one thing we could do is take this row and divide by 6. Another thing we can do, though, is since the third row has a 1 in the first column, is we can take these rows and switch them. So that's what we'll do. We'll take row 1 and swap it with row 3. So So you get 1, 0, 2, 3, 0, 2, negative 6, negative 8, and 6, 3, negative 2, negative 4. Even just copying the matrix when doing this process can cause little tiny mistakes if, say, you miss a negative sign or you look at the wrong row for a second. And so if we take a look at this matrix, what we have right here is a 1 here, and that's a leading 1. Great. So what we want to do is we want to be able to get below it zeros. So in order for this to be a leading 1 and for us to get this up to the triangular form, we need a 1 here, zeros below. So this entry already has a 0. This entry we still need to make a 0. So in order to get this to be a 0, we're going to take row 3 and make it equal to row 3 minus some multiple of row 1. Now the reason it's so nice that this is already a 1 is what do we have to multiply 1 by to get 6? Well, that's easy. It's 6. So we'll take row 3 and subtract 6 row 1. So when we do that, we still leave row 1 and row 2 the same. Row 3, however, we'll take whatever entry is here and we'll subtract 6 times the entry here. So this will be 6 minus 6 times 1, which is 0. Great. Then we'll take 3 minus 6 times 0, which will still be 3. We'll take negative 2 minus 6 times 2. So let me pull out a calculator here just so we can see what's going on. We'll take negative 2 minus 6 times 2, and we get negative 14. And last but not least, we'll take negative 4 minus 6 times 3. So we'll get negative 22. Alright, so we've gotten the 1 up here, and we've gotten zeros below. What we'd like to do next is get a 1 in this position. So this is the thing we want to target next to make a 1. Now, when we take a look at our two things we can do, swapping rows or multiplying some row by a scalar, what we'll notice is that there's not really a 1 in this column that we want to use. So we're going to go ahead and take this row and multiply it by a scalar. So the question is, what do I have to multiply 2 by in order to get 1? And the answer to that is a half. So we'll take row 2 and set it equal to row 2 times a half. Alright, so continuing on, we have 1, 0, 2, 3. Half of 0 is 0. Half of 2 is 1. Half of negative 6 is negative 3. And half of negative 8 is negative 4. And then row 3, for now, remains unchanged. Okay, so now we have our 1, and we'd like to make this entry into a 0. So, since we want to get a 0, what we'll do is we will take row 3, where this 3 is that we want to make a 0, and set it equal to row 3 minus some multiple of row 2. Again, since we already have a 1 here, it's easy to figure out what we need to multiply it by that in order to cancel out the 3, and that's just negative 3. So as we continue then, we get 1, 0, 2, 3 from before, 0, 1, negative 3, negative 4, and then the last row. Now for each of these, I'm going to go ahead and kind of set the calculator next to us so we can kind of verify. What we're doing is we're taking the entry in row 3 and subtracting 3 times the entry in row 2. So 0 minus 3 times 0, probably didn't need a calculator for that. That'll end up being 0. Next entry will be 3 minus 3 times the entry above it, which is 1. So that'll give us 0. Next entry is negative 14 minus 3 times, looks like the entry above that is negative 3. So we'll get negative 5. And the last entry will be negative 22 minus 3 times negative 4. And so that'll give us negative 10. Okay. So now we've got this one that has zeros below it. We have this one that has zeros below it. And now we want to go ahead and take this entry and turn it into a 1, since it's the leading term. So let's go ahead higher up on the page for the next step. So we want to take this, and if we want to take this negative 5 and turn it into a 1, well, that means we'll take the third row and set it equal to the third row times negative 1/5. So when we do that, again, we do not change the other rows. 1, 0, 2, 3, 0, 1, negative 3, negative 4, and 0, 0, 1, 2. Okay, so just to check, we've gotten into echelon form now, and we have all of these leading ones that we can work with. So now that we have these, we're now done with the first step. We've got an upper triangular form matrix. We now need to get into reduced row echelon form by eliminating anything that's above our leading ones. So in this case, we just need to get rid of the negative 3 and the 2. So we can change both row 1 and row 2. So row 1, because we have this 1 here, will become row 1 minus 2 row 3. And row 2, take a minute to see if you can figure out for yourself what the row operation will be. Okay, great. So row 2 will become row 2 plus 3 row 3. So if we do that, we want to make sure that we can change each of those entries. And so row 1, the first entry will become 1 minus 2 times whatever's in row 3, which is 0 in that spot, which is 1. The last entry, or the next entry, will become 0 minus 2 times 0, which is 0. You might ask yourself, well, if I know these are zeros, do I really need to be doing these steps? The answer is, it helps for practice sake. Next entry should be 2 minus 2 times 1, which is 0. The glare from the calculator's catching us there. And the next entry will be 3 minus 2 times 2. And so that'll give us negative 1. Alright, now we said we also wanted to change row 2. So row 2 will become 0 plus 3 times 0, which is 0. 1 plus 3 times 0, which is 1. And negative 3 plus 3 times 1, which is 0. And then negative 4 plus 3 times 2, which is 2. And then our last row stays the same. So now we've got reduced row echelon form. So what's neat about this is we essentially just did all of our steps for elimination and substitution and such in order to get what this final form is. So now we want to be able to take out the matrix and read it as equations. So let's pretend our variables are x, y, and z. So we'll say then that x equals negative 1, y equals 2, and z equals 2. And so that would give us the solution, negative 1, 2, 2. Either one of these ways to write this form is absolutely fine. Some questions we could ask going forward about linear systems is whether or not our solutions even exist, and how many solutions we have. So let's ask ourselves about some of those questions. So what we'll do is we will go ahead and take our Gaussian elimination reduced row echelon forms and convert things back into systems of equations in order to determine how many solutions we do have. So for these examples, we're going to go ahead and pretend that our columns are x1, x2, and x3. Take a minute to pause the video, and so I can take a drink of water, to see if you can determine what these solutions are going to be on your own. Alright, great. So, let's take a look at these solutions. So here, we're saying that x1 equals 2. Second row says x2 equals 0. And the last row says x3 equals negative 3. So we have one solution, and the solution is 2, 0, negative 3. If we want to take a look at our next equation, we're saying that we have x1 equals 2, x2 equals 0, and the last thing says 0 equals 0. Now, we can write this, but it's not really all that helpful to us. It doesn't tell us anything. However, what you'll notice is that x3 is a free variable. So, since x3 has no leading terms, it is a free variable. So we have a few ways we can write this. We can say then that x3 equals x3, or we can say x3 is an element of the real numbers. The short answer, or the short version, is it can be anything. You ever grow up and your parents tell you can be whatever you wanted to be? Well, x3's parents told it could be whatever it wanted to be, and it did. It can be whatever. So the way we write this is we have the set of all solutions 2, 0, x3, where x3 is an element of the real numbers. So if it's possible for x3 to be anything, here we'll have infinitely many solutions. Okay, now let's take a minute to look at this next set of equations. So we have x1 equals 2, x2 equals 0. Now this last row is a little weird. It says 0 equals negative 3. Is 0 equal negative 3? No. This is not true. So because we have a statement that's not true, we have no solution. Okay, and then our last system has the equations x1 plus x3 equals 2, x2 equals 0, and 0 equals 0. But you'll notice, similar to before, x3 has no leading terms. So because of that, it's a free variable. So then we say x3 equals x3, or in other words, x3 is an element of the real numbers. It can be whatever it wants. And so we have infinitely many solutions again. And so a system of equations can have either infinitely many solutions, exactly one solution, or no solutions. So a system is called consistent if it has one or infinitely many solutions, and it's called inconsistent if it has no solutions. So let's go ahead and quickly try to solve two more systems, just to give a little bit more of examples of Gaussian elimination. So first we need to take this system of equations and write it as a matrix. So if you notice here, similar to our example before, if we have x1 plus x2 plus x3 equals two different things, we should expect no solutions. But we can see this out of the matrix form as well. So 1, 1, 1, 4, 1, 1, 1, 0. So remember, in Gaussian elimination, we want to go ahead and take and get leading ones, and then eliminate the things below as our first step. So we want to go ahead and use this one to get rid of this one. In order to do that, we will take the second row, and in order to get a 0, we'll take row 2 minus 1 times row 1. This will end up getting us 1, 1, 1, 4, and 0, 0, 0, negative 4. But if we take this and rewrite it, this last row will say 0 equals negative 4, but that's not true. So because of that, because of this, we have no solution. Okay, so we can see where we get no solutions for one of our answers. So let's go through one more example before we kind of give you free rein to try some more stuff on the ice. And we'll try to solve this system of equations using Gaussian elimination. So remember, we have two steps we want to do after we get the matrix. First step is to get that form with the leading ones, that echelon form, and then step 2 will be for us to go ahead and end up with reduced row echelon form. Alright, so first we should take and write this as a matrix. So if we write our coefficients, we have in the first row 2, 2, 2, 4. The next row says we have negative x plus 1y minus 2z equals negative 2. And our last row says we have 1x plus 1y plus 1z equals 2. Alright, now from here we want to go ahead and be able to get our leading ones. So remember, you can do this multiple different ways. So what I want you to do is I want you to determine how you would like to solve this problem, do that, and then come back to the video, see what I do, and see if you get the same solution. Alright, did you get a solution? Let's see if you're right. So what I want to do is I want to go ahead and take this 2 and turn it into a 1. I could use the 1 from down here, but I'd rather just take this and divide it by 2. So I'm going to take row 1 and set it equal to 1/2 times row 1. So here we'll get half of 2 is 2, half of 2 is 1, half of 2 is 1, half of 2 is 1, and half of 4 is 2. Get negative 1, 1, negative 2, negative 2, and we get 1, 1, 1, 2. So now that we have this 1 up here, we want to be able to eliminate these ones and get zeros below. And so we will change both row 2 and row 3. So row 2 will become row 2. If we want to go ahead and get these to cancel, we need to add row 1 in order to get that 0. And if we want to go ahead and be able to take row 3 and get rid of the 1 there, we'll take row 3 minus row 1. So if we do that operation, we should get 1, 1, 1, 2. Row 1 doesn't change. We'll end up with 0, 2, negative 1, 0, and 0, 0, 0, 0. Okay. So, our next step, since we have this leading one figured out, is we'd like to get a leading one here, if we can. So, what we'll do is we'll take row 2 and set it equal to 1/2 of row 2. And so when we do that, first row does not change, 1, 1, 1, 2. Second row becomes 0, 1, negative 1/2, 0. Last row becomes 0, 0, 0, 0. Alright, so we have our leading 1. And we want to go ahead now, since we're in echelon form, and take out any leading ones or any other non-zero terms above any leading ones we have. So this 1 is the only term we need to go ahead and take out. So moving up here, slide the page, we'll have row 1 equals row 1 minus row 2. And performing that will give us 0 or 1, 0, 3/2, 2, 0, 1, negative 1/2, 0, and 0, 0, 0, 0. So here, this is in reduced row echelon form. So taking a minute to inspect what we have, these are our leading ones. Now x3, z has no leading term. So z is a free variable. So when we take this and we rewrite it as a system of equations again, the first row says x plus 3/2 z equals 2. Second row says y minus 1/2 z equals 0. And the last says 0 equals 0. So we know that z is free. And so when we want to write our solution set, what we're going to do is we're going to rewrite it so that anything that's not free is on the left, and anything that is free is on the right. So we'll have x equals 2 minus 3/2 z, and we'll have y equals 1/2 z. And remember, z is just going to be z. It's whatever it wants. It's free. So as we write our solution set, we'll have the set of all 2 minus 3/2 z, 1/2 z, z, such that z is an element of the real numbers. So you can write this way, or, a little more complicated, you can write it as 2, 0, 0 plus z times -3/2, 1/2, 1, where z is an element of the real numbers. So both of these are saying the same thing. We're saying that z is allowed to be whatever it wants, so in that third position in the vector, we need to make sure we're talking about the z portion, and then x can be described as -2 minus 3/2 z, and y can be described as 1/2 of whatever z is. And so this form separates out the constant parts and the parts that are being represented by the free variable, and this puts it all into one big mess. I don't have a preference as to which one you use, but it is important to actually make sure you're using both of these, or one of these, when you go ahead and write your solutions. So that way I can know you're kind of making sense of it.